Cool. So now that we have that, we can redraw the picture they give us in the book, and we can set our potential energy equal to 0 through the center of mass of the cart, so that we just have to worry about the spring force, and the height of the mass will be a negative h, and that will be important when we try and find our Lagrangian. So for just the cart, we know that its velocity is just in the x direction, so x dot is all we need, and only potential energy is the spring force. But for the pendulum, it gets a little complicated. The potential energy, as we said before, is negative because it's below the u equals 0 line, and if we draw our triangles, we can see that h equals L cosine phi. We can plug that in for h, and we get a negative mgl cosine phi. And the position of the mass is the distance the cart has moved plus the swing of the pendulum. And so our x position is just how far the cart has traveled plus our L sine phi of the swing of the trajectory of the pendulum. And the y position is L minus L cosine phi, so the full length minus however high it swung up from the angle. And we take the time derivative to find velocity. And since velocity squared is a dot product, we know we can just square our individual parts and add them together. So there's v in the x direction squared and v in the y direction squared. And we can add them all up. And we see that we have a cosine squared and a sine squared, so we can factor out that L squared phi dot squared and turn our cosine squared and plus sine squared into 1, and we get this equation for our v squared overall. And so now we can combine all the previous parts into our Lagrangian, which is t minus u. So t of the pendulum plus the cart is this is just for the cart, and this is for the pendulum, and potential energy, this is for the cart, this is for the pendulum, and we know that we need to use a small angle approximation to get rid of the cosines, and so cosine phi equals 1 minus phi squared over 2. But since this cosine phi here is added to other things, we don't care about the quadratic part because it's going to be too small to matter because we have other squared things, so that's going to get rid of that. So, but here, for this cosine phi, we're going to have to keep the quadratic term. And so here's our total kinetic energy and our total potential energy. And so combining our results from the previous part, our total Lagrangian is the total kinetic energy minus the total potential energy, and I went ahead and distributed that minus through. And now we can Euler Lagrange this. We need one equation for x and one equation for phi, so here's the one for x, or here's the partials for x, and here are the partials for phi. We now have to take the time derivative of the ones with dots on them. So for the equation of motion for x, we have negative kx equals time derivative of that, which gives us that equation. And for phi, we have negative mlg phi, and then time derivative of that, which gives us this. And so here are equations for x and phi, the motion in those two directions. To turn those into one matrix equation, and usually motion equations take the form of this, with m times something with a double dot and something times just the variable. And so if we distribute through our two equations to separate the x double dots and the phi double dots, we can see that a little bit clearer. And so for our matrix, x only depends on k, and phi only depends on mgl, and I went ahead and factored that negative out because that's the form of our equation. And then these just line up really nicely, and we get that. And so now that's our K matrix and that's our M matrix. So when we try and do this to solve for the normal modes, we can just subtract our M matrix from our K matrix, but first we have to multiply the M by omega squared. And so here's that. K minus omega squared M for all of these, and I changed these to amplitudes now. And we're given that the mass of the cart equals the mass of the pendulum, and that equals the length of the string, and that equals gravity, which nicely all equals 1, and the spring constant 2. So if we plug that all into this matrix, we get this simplified, and that we know has to equal 0. And I just went ahead and wrote that same matrix up on top so I'd have it. So when we do the determinant of this, which makes it equal 0, you can see that we're going to have to use the quadratic formula. And so there are my steps for that. And we end up with 2 plus or minus root 2 equals omega squared. So that means we've got 2 normal modes. And so I just made this one normal mode number 1 and this one normal mode number 2. So normal mode number 1 is just the plus root 2, number 2 is just the minus root 2. And to solve for the motion in these normal modes, we're going to plug this omega squared back into our matrix here. So let's do it. And so for normal mode number 1, we can simplify a little bit and do the matrix multiplication, so top and then bottom, and we combine them, and we see that negative root 2a1 minus a2 equals 0, and we know that a1 represents the pendulum bob's motion, and so our final answer would be that root 2a1 equals negative a2, which means that the motion is out of phase, and the amplitude of the pendulum will be root 2 greater than that of the cart. And so for normal mode number 2, we'll do the same thing. Plug in 2 minus root 2 for omega squared, and then simplify all the way through. And then we get that root 2a1 equals a2, which means that this motion is in phase, and the pendulum's amplitude is still root 2 bigger than that of the cart's. Cool. Thanks for watching.